thanks everyone for coming. This is great. We've got dozens of people here, which is pretty good, I think, for a remote seminar. And so just I guess I could give an introduction to the collab. This is the Materials Collaborative, or ACME Alabama Collaborative for Materials Exploration, which is something we're trying out. I think Adam should really be the one to say more, but we're trying to bring people together to talk about different aspects of material science. Today we have Professor Nee from UCLA in the Department of Physics there. She's an associate professor there before in the Department of Physics, working on like solid state materials, condensed matter physics, electronic properties. Before that, she was at Los Alamos as a Marie Curie fellow. Is that right, Nee?
Yes, right.
And then before that, she was a postdoc in the Kava group at Princeton. That's where I know her from about 12 years ago now. Doesn't feel like that long ago, but
was that 12? Wait.
Well, what's when you joined in 2000? Was it 2009?
Yeah.
Sorry.
Oh my gosh. Okay.
Yeah.
Best not to dwell on these things.
Yeah, sorry, I didn't mean to. But anyway, and then she did her PhD with Paul Canfield at Ames Lab at Iowa State. And there I don't know how many people in the room have looked at iron-based superconductors, but I think that, basically a huge fraction of the early work on iron-based superconductors, if she didn't do it, it was done on her samples that she had made. So, and then after that, she was in the Kava group. That's where I know her, one of the physicists who taught me a lot. And now I'd say she probably makes more samples than I do, even though I'm in chemistry. I think she does more chemistry than I do. So she makes stuff, she measures properties, and I'm really excited about today's talk because it looks like it's going to give us a lot of chemistry and physics. So, and hopefully more. So I think that's enough introduction. We'll make sure you have time to talk. So I'll get out of the way.
Okay, great. Okay, should I start? Thanks for Jared's nice introduction. And I remember we had a very nice collaboration on the 1038 sample, right? So I made a material, you solved this mission impossible crystal structure, and then we made a good work on it. It's nice that I got invited to give the talk here. And especially I noticed that it is the Alabama Collaborative for Materials Exploration, right? So I have to say that all my research are based on big collaborations. So I won't be able to do anything without my nice collaborators. So in my proposal review, you can clearly see, almost every reviewer says that she has a fantastic, amazing collaborating network, and which is really, one of the major advantages for my proposal. Okay, so today my talk is going to be about the so-called manganese-bismuth-toluene intrinsic topological insulator family, and a happy marriage of magnetism and topology. So initially my talk was a perfect marriage. And then after 2 years of study, I decided in the world, there is no so-called perfect marriage. However, a happy marriage is good enough. You will say that. Okay. So first, I would like to acknowledge my collaborators and my student. So the single crystal growth and the bulk characterization was done by my graduate student, Chao Wei, and APA's measurement was in close collaboration with Dan Dassault's group. And some of the data for the 124 was in collaboration with USTSC Chang Liu's group. And neutron scattering work was done with the collaboration with Hui Bo Cao's group at Oak Ridge National Lab. And I have lots of theory support, and especially from Tyrone Chang. And for Igor, it was based on the collaboration was on the magnetism, and then Su Yang, Qihang, Aaron, Darren, etc. Yeah, without my collaborators, I won't make it happen. So the talk will have 4 parts: motivation, and then I will talk about the MBT first family of intrinsic magnetic topological insulators. And then I will talk about the antimony doped 147. And so that we can start, which is about tuning the magnetism and topology through antacid engineering. Okay, so quantum alarm Hall effect describes a phenomena where quantized dissipationless Hall conductance emerges under zero magnetic field. So after the discovery of the 3D topology insulators, it was proposed that if the topologically protected Dirac cone here can be gapped by magnetism, then in its two-dimensional limit, right, the chiral edge state, which is QAH effect, will appear in the gap. So in 2013, QAH was experimentally observed in chromium-doped topological insulator thin film below 30 millikelvin. So the thin film actually it orders ferromagnetically below 15 Kelvin. However, the effect was observed below 30 millikelvin. So this low temperature required to realize such a QAH effect is actually due to the sample inhomogeneity in doped materials. So then the question is how to realize QAH at elevated temperatures. There are lots of trials, for example, to make this sample even less inhomogeneous, etc. But 30 millikelvin was enhanced to up to maybe 300 millikelvin. However, it was still always, we want even higher, right? So how can we have the QAH effect at an even higher temperature? Then the answer is new. The other way to think about it is rather than improving the old material, but rather we just look for new materials. What type of new materials? The new magnetic topology insulators whose magnetism is intrinsic rather than being doped. So however, make such a material realization was very challenging. So finally, later, back in 2018, like 5 years later, manganese bismuth 2 tellurium 4 was discovered as the first intrinsic antiferromagnetic topology insulators. So it was made by this so-called 1-2-4 subtuple layer building block, right? So it orders below 24 Kelvin. It orders below 24 Kelvin with an so-called A-type antiferromagnetic structure that is spin ferromagnetically aligned in the AB plane, but antiferromagnetically coupled along the Z-axis. It has a spin flop transition. You can see it has a spin flop transition around 3.5 Tesla and a saturation field around 8 Tesla when the field is applied along the Z-axis. So although this is an antiferromagnetic, because it has this A-type antiferromagnetism, so as I said, it is the AB plane is ferromagnetic aligned. So therefore, the theoretical proposals proposed that QAH effect can be realized in all the layers of 1 to 4 in its 2D limit. Once it's odd, then you will have a overall ferromagnetism in that device. Everybody worked really hard and the field moves really quick. Just a half a year later, QAH was actually observed at a zero field below 1.6 Kelvin in a 5-layer 1 to 4 device. This value you can see is orders larger than 30 millikelvin in the chromium doped thin films, right? And later on, the quantized Hall conductance is also observed when the device enters into false ferromagnetic state under external fields. For example, you can see when it is 3-layer, 4-layer, 5-layer, 7, 8, and 10 layers. So the quantized Hall conductance will actually, emerges about 8 Tesla up to even 10s of Kelvin. So it's really a pretty high temperature. So it's very exciting progress. It seems like the dream came true, right? But can the dream be even sweeter, right? So can we make intrinsic antiferromagnetic the topological insulator with smaller saturation field. So if we make smaller saturation field, then the field induced the quantized Hall can be observed at lower field rather than 8 Tesla, right? Or even sweeter, can we make intrinsic ferromagnetic topological insulators so that the QAH effect can be realized at 0 field and high temperature? So since my group focuses on the design and the material synthesis of new materials, then our goal here is we want to look for such a material realization of antiferromagnetic topological insulators with smaller saturation field. We want to look for material realization for ferromagnetic topological insulators. So that's our initial goal here. Okay, so now, so before we go forward, so the saturation field, this material has uniaxial anisotropy here. The saturation field depends on the interlayer exchange interaction and the magnetic crystalline anisotropy here, right? So you can see there will be 2 strategies to go for that, which means it's either you tune the exchange interaction or you tune the magnetic crystalline anisotropy. So this is the crystal structure of the 124, right? One strategy is to increasing the distance between these 2 layers, right? By increasing the distance between these 2 layers, you will be able to reduce the interlayer exchange interaction, right? So how can we increase the 124 interlayer distance? One way we can do is we can by introducing spacer layers between them. So that's the strategy 1. And the strategy 2 is we can doping the 124 plane to change the local manganese environment. So by this way, we may be able to increase the anisotropy parameter, or we may introduce some magnetic dilution effect. We don't exactly know. However, there will be a chance that we can change by doping the 124 layer, we will be able to change the manganese local environment. So in the first part of the talk, I will show you following the first strategy, how we discovered the first intrinsic ferromagnetic topology insulator. And in the second part of the talk, I will show you how we tune the magnetism and topology by the second material design strategy. Okay. So for the first strategy is, the first question is, what type of spacer layers can be inserted between 2 124 layers, right? So if we look at the ICSD database, we can say the 124, manganese 124 actually takes the same crystal structure as the germanium 124. So in the ICSD, we noticed that a Lego set of this germanium 124 and 0 to 3 actually exists. So germanium bismuth 4 tellurium 7 actually exists. Then the natural question is, it seems like 0 to 3, which is the bismuth 2 tellurium 3 layer, should be able to work fine as the spacer layers. Therefore, if I have one of these spacer layers, right, I will be able to make a compound which is the so-called 147. And if I have 2 of these spacer layers, I will be able to get the 1610. And if I have 3 of these spacer layers, I will be able to have the so-called 1813, right? So there was actually no single crystal growth and the physical property measurement on these materials when we started the project. So can we make high quality manganese bismuth tellurium single crystals? Are they antiferromagnetic or ferromagnetic? And then what's their topological classification, right? So that's all the questions we have. Okay, great. So it's time to cook, right? So we use the flux method to grow the sample. We mix sample and we seal them under 1/3 of atmosphere of argon. We put it in the furnace. After the synthesis, we spin out the liquid from the single crystal. And the most important part is we need to have a very happy patient, graduate student with a magic hand, happy, right? It turns out as this is a very challenging synthesis project, right? So my patient, I have a very good graduate student, Chawi. He found that the growth window for this metastable phases are within several degrees, around the 590 degree. So it turns out like for 147, the growth window is around 2 or 3 Kelvin, and then 1A13, the growth window is even below like 1 Kelvin. So he has to do a lot of trial and error synthesis to find the sweetest spot in the furnace, so that he can get 147, 1610, 1A13. Okay, so after we got single crystals, now let's take a look at the magnetic properties. So here is the magnetic property of the 124, right? As you can see, we have a spin flop transition here. And then this is a comparison of the magnetic property for the 147. So you can clearly see that the 147, you can see it does not have this so-called spin flop transition, but now you have a first order spin flip transition, and the saturation field is just 0.22 Tesla, which is almost 40 times smaller than that of the 124 compound. This actually suggesting the success of our material design strategy here. Okay, so now I showed you the magnetic property measurement about the 1610. Okay, so 1610, you can see it is also shows a antiferromagnetic behavior here. The saturation, it has a first order spin flip transition with the saturation around 0.2 Tesla. So, and the easy axis is still C axis. So now, if we look at 1A13, we immediately see a difference between 1A13 and all of the others, right? So here, instead of having a little cusp here as the 1610, which shows you it's an antiferromagnet, for 1A13, we saw a very large bifurcation in the zero field cool and field cool data. And also, if you look at the field cool data, the magnitude here is like 10 times larger than 1610. So furthermore, if you look at the MH data shows a typical hysteresis loop for ferromagnetic material. There is no indication of a spin flip transition here. So you can see the 1A13, it seems like from our measurement, it looks like ferromagnetism rather than an antiferromagnetism. There is actually strong coupling between magnetism and charge carriers. So the magnetism, if you look at the band structure, the magnetism, like the manganese band was way below or above the Fermi level. And at the Fermi level, it was mainly the bismuth and the tellurium bands. However, even for that, we saw strong coupling between the magnetism and the charge carriers. This is the 147, this is the 1610, 1A13. You can see for all of them, the rho x-axis, which is the current along the AB plane. The rho x-axis shows very similar behavior, which is below the transition temperature, the resistivity decreases, right? Which is reasonable because within the AB plane, spins are paramagnetically aligned. So once you enter into the ordered state, you lost your spin disorder scattering, right? However, if you look at the ZZ, which is when your current is along the C direction. So for 147 and 116, you can see your resistivity actually increases in the ordered state. That just suggests the reduction of the loss. Actually, it just means the increase of the spin disorder scattering. So if it's that's again, it's consistent with the fact that along the C direction, the spins are actually antiferromagnetically aligned, right? So if you look at 113, even for those ZZ, in the ordered state, the resistivity actually drops. So this is a second evidence saying that the 1A13 along the C-axis, the spins are aligned parallel with each other, and along the AB plane, the spins are aligned parallel with each other. So both of that, both the magnetization measurement and the transport measurement suggest that we have a ferromagnetic compound here. And then Hui Bo from Oak Ridge National Lab did single crystal neutron diffraction measurement. So he was able to figure out the crystal structure of the 1A13, which was never the 1A13 was never discovered before, and therefore there was no crystal structure information. And he also was able to find that there was actually manganese deficiency on the manganese side. So if you can see for the pure 124, you have 18% of deficiency on the manganese side. And once you go to even higher N number, you can see it drops the deficiency, the vacancy increases from 18 up to 36. So his neutron scattering measurement also shows that the magnetism here is a 3D magnetism, despite their van der Waals crystal structure here. So therefore, now you can see we have a natural heterostructural family with great tunability to investigate the interplay of band topology and magnetism here, right? So we have this is a very tunable system. So what's the topological nature of it, right? So to identify its topology, DFT calculations and APAS measurements were performed. So you can see for the 147 and the 1A13, we can clearly see there is band inversion around the gamma point. So which is an indication of possible topological phases. And then our collaborators calculated the topological invariant Z2. And for both 147 and 1610, they got a Z2 number as 1. So this suggests that they are Z2 antiferromagnetic topology insulator. And for manganese bismuth 8 tellurium 13, so although the Z2, so because for this somehow it's ferromagnetic, so therefore the time reversal symmetry was completely broken. So Z2 invariant is no longer well defined, but the Z4 invariant, which is well defined here, it equals to 2. So if Z4 is odd, it indicates a wild sum middle phase. And if Z4 is equal to 2, it actually corresponds to an insulator phase where a quantized topological magnetoelectric effect can actually occur. So 1A13 was identified as a ferromagnetic axion insulator by the DFT calculation. So now next is, you have so many elements in one unit cell, right? So how trustable the DFT calculation will be, right? So then we approached with Dan Dassel. he's an expert on APAS measurement, and his student and him did a fabulous work in imaging the APAS of the band structure of this materials by APAS measurements. So if we look at the crystal structure of all of these compounds, right? So you can say this the blue slab means it's a 0 to 3 layer. The purple one means it is it's a pink one. The pink slab shows it is the 1 to 4 layer. Okay, we call the 1 to 4 layer as the SL layer. The blue slab as the QL layer, because this one has like 5 layers of atoms. This one has 7 layers of atom. So So now, if you look at 147, you have 2 different layers. If you look 1610, you have 3 different layers. If you look at the 1813, you actually started to say 5. Yeah, you say 4 different layers. Because within 2, 1 to 4, you have 3 different 0 to 3s. So that just means for 147, if you do APAS, which means if you do APAS, you will be able to cleave on 2 different layers. If you do APAS on 1610, you will be able to cleave on 3. And if you do it on 1813, you will be able to cleave on 4 different layers. And indeed, this is what Dan saw. So for 147, he has done very careful APAS measurement using a beam size which is around 10 micrometer to 20 micrometer size. So by that way, he was able to identify 2 distinct surface states for the 147, 3 distinct surface states for 1610, and 4 different surface states for 1813. Okay. So this picture shows the comparison between the APAS measurement and the DFT calculation. You can say when I first got the data, even if I was not an expert on this DFT or APAS, I immediately saw the similarities between the calculation and the experimental data, right? So because this, the agreement between them is just amazing. So look at the lobes and the subtle features. So although the calculated band gap value is smaller than that from the APAS measurement, it is actually well-known problem in the generalized gradient approximation calculation, because usually the GGA calculation will produce a band gap which is smaller. So this excellent consistency between APAS measurement and the DFT calculation just assured us that we are looking at the right layers and the parameters in the calculation. So therefore, that is a indication saying that the DFT calculation the DFT calculation captures the real material. Okay, so something I want to draw your attention, which is about the, if you look at this, if you look at all of them, right, you can see for this kind of a QL1 layer, which is the layer just on top of the 124 layer. So if you look at this 147, 1610, and 1813, you can see for the QL1 layer, they show the largest mass gap here. They show the largest gap, like around 100 millikelvin or even higher, right? So the larger the gap, which just means the more stable, if you will be able to realize QH, that just means the QH will be able to realize at a high temperature, and it will be pretty stable. Okay, but then we realized this large gap. Initially, we thought it is a Dirac gap which was gapped, but then after a closer look into the DFT calculation, it turns out this large surface gap, this large surface gap is not a gap, the Dirac cone, but rather it's a so-called hybridization gap induced from the hybridization effect between the SL layer and the nearest neighboring QL layer. So we can say from this simple toy model here, right? So here the MZ is the Zeeman splitting energy, and the VH is a parameter describing the hybridization strength between the QL1 layer and the SL layer. So you can say at MZ equal to Z and VH is equal to 0, we can say you can say what you have here is a Dirac cone, and then you have this blue band, this purple band, which is from the SL layer. And then when you turn on the MZ, the Zeeman splitting energy, you started to say there is a little gap. There is a gap, right, on your Dirac cone. So you gapped your Dirac cone. However, when you turn on the VH, which is the hybridization gap, you can see besides the Dirac cone gap, you started to have an extra gap. This extra gap is the so-called hybridization gap. And this hybridization gap is what we observed in our experiment here, this large gap here. This is the hybridization gap. So then the next question is, because like at the beginning we say, if we want to realize QAH, we want to open a gap at the surface Dirac cone. So now the problem is we have a large gap, large surface gap, but it's not a gap on the surface Dirac cone, but rather this is a large gap, a large hybridization gap, right? So can this hybridization gap persist and support QAH in the 2D limit? Then Tyrone performed a DFT calculation on a 7-layer slab structure that has the QL1 termination on both surface sides. And it turns out that this surface gap actually persists even inside this 7-layer slab structure. And furthermore, it turns out this gap is non-trivial, and which will still support the QH and QME effect in the slab. So this result actually opens a new door for the material realization for QH. That is, not only a Dirac gap can host the QH, but also a hybridization gap from a Dirac band and a magnetic band may host the QH too. Okay, so our last comment here for this MBT family is, because I want to emphasize this family of compounds is they are natural heterostructures, right? So which means when you do exfoliation, you will be able to get the heterostructure just by exfoliation rather than, you do MB grows, you grow one layer, they grow the other layer. No, we have this bulk material, just by exfoliation, you will be able to have a different combination of the QL and SL layer here. So you can see here, A means the SL layer, B means the QL layer. So with different combination of A, B, B, A, right, you will be able to realize different like QAH state, QSH state, etc. here. So this family of compounds just provide a really a huge playground for the 2D device society to play with them. Okay, so the next part of my talk is going to be antimony doped 147. As we talked before, right? So this is based on the material design strategy of the second part. Like initially, what we want to dope antimony onto the 1 to 4 plane so that we can see how can we change this anisotropy parameter so that we can change the magnetism inside this material. Okay, but before I go further about the antimony doped 124, I want to introduce some background on this so-called antacid disorder. So that's what I said. It's a happy marriage, but it's not a perfect marriage. Why is that? You know, so for material design, you always thought, or in theory calculation, right? You say, oh, manganese should be at the manganese side, bismuth should be at the bismuth side. But in reality, when we grow samples, right, there could be deficiencies, there could be antacid disorders. It turns out for this family of compounds, a recent publication from Oak Ridge Liaison Lab, they were able to show that based on the high magnetic field, based on the high field measurement, they were able to show that the 124 compound has 1% to 2% of antacid disorder. And the manganese antimony 2 tellurium 4 has 13 to 17% of antimony to manganese antacid disorder. So what is the antacid disorder? Which just means manganese and bismuth will exchange. So there will be some bismuth. There will be some bismuth on the. There will be some manganese on the bismuth side. There will be some bismuth on the manganese side. So we call the manganese on the bismuth side as the manganese 2. Okay. So therefore, if the neutron scattering shows that for the 124, when you dope more antimony, when you dope antimony inside, as you can see, when you dope antimony inside, because of the smaller radius difference between manganese and antimony, they tend to form a larger antacid disorder, right? So from the study of this manganese antimony 2 tellurium 4, which is the extreme case here, they found that the manganese 2 sides always be antiferromagnetic coupled with the manganese 1 side. They found that if there is less antacid disorder, the manganese 2 sublattice by itself, right? By itself, it is antiferromagnetic coupled. Manganese 1 sublattice by itself, it is antiferromagnetically coupled. Manganese 2 and manganese 1, they are these two individual sublattices are antiferromagnetic coupled with each other. However, once you have more antacid disorder, your sample becomes like ferromagnetic-like. Okay, it becomes like ferromagnetic-like, as you can see that. And once you have more antacid disorder, your manganese 2 becomes ferromagnetic ordered. Your manganese 1 becomes ferromagnetic ordered, but still the manganese 1 and manganese 2 are antiferromagnetically ordered. So this was a little background here. Okay, so now when we dope antimony into the system, we found a pretty rich and complex evolution of magnetism. So when it was 13%, right, you can see we started to see an extra magnetic phase transition here. And when we increased the doping level, we saw this extra magnetic phase transition. It turns out it looks like a ferromagnetic type, and it was moving to higher temperature. And finally, these two ordering temperatures merges together. Okay, so here is, you can see this is the summary of our data, right? So besides this additional ferromagnetic-like transitions at the TC, right? Furthermore, if you look at the MH data, we found that the saturation moment with doping are actually decreasing, right? I will say the moment around 7 Tesla, it was decreasing. It decreases from 4.4 EMU per manganese down to 3.2 EMU per manganese here. So what happened here, right? So why does the antimony doping introduces this rich and complex magnetic evolution in the 147 compound? So let's take a look at this crystal structure for 147. So compare with the 124, right? 124, it will have a manganese 1 sublattice, it will have a manganese 2 sublattice. So manganese 2 sublattice was made with arises because of the manganese antimoney anticides, because manganese goes to bismuth site in the 124 layer. However, for our 147, we have one more extra 0 to 3 layers, right? So therefore, we will be able to say the manganese goes to the manganese site in the 0 to 3 layers, which will produce a third, one more extra manganese sublattice. We are going to call it as manganese 3 sublattice. So you can think about that is from the magnetization, right? We saw the saturation moment decreases with antimony doping, which is kind of consistent with the fact that we can think that when we dope more antimony, naively thinking we will have more manganese anticides and more manganese anticides, which means we will have a increasing concentration of manganese 2 sublattice and manganese 3 sublattice, right? So, and then if you look at the 2 different concentrations, right, you can say, okay, right? So if we think about that, we will say between the TC and the TN, right, between these 2 phases, we are entering into a so-called ferromagnetic and antiferromagnetic ferromagnetic case. Right? What does that mean? That just means your manganese 1 sublattice is antiferromagnetic to itself. Your manganese 2 sublattice is antiferromagnetic to itself. And these 2, manganese 1 and manganese 2, they are antiferromagnetic to each other. And then once you enter into this ferromagnetic state, right, you started to have this so-called ferromagnetic phase, yeah, which means your manganese 1 sublattice will be parallel to each other, manganese 2 will be ferromagnetic. However, the coupling between these 2 sublattices is going to be antiferromagnetic. So we believe that's what happened here, right? But then the next question is, yes, it's all natural, right? To just based on the knowledge on the manganese antimony 2 tellurium 4, come down to the knowledge, to the understanding or the hypothesis of the magnetic structure of the manganese 1 and manganese 2 in this doped 147. But then the next question is, how does the manganese 3 order, right? How does the manganese 3 order? Okay, then we performed the single crystal neutron defection at the 0 to 0 at the 76% doping level. It turns out that yes, indeed, based on our magnetic property measurements, right? Indeed, the manganese 1 and the manganese 2, the magnetic state are just the neutron scattering measurement are consistent with our hypothesis. And then from the neutron scattering, one very interesting thing is the manganese 3 moment are actually, the observation for the manganese 3 moment is actually, it's very small. It's almost a 0 within the experimental error bar. So that just suggests that the manganese 3 here is either paramagnetic or just a glassy here. And our recent AC susceptibility measurement shows there was no relaxation behavior about 500 oystat. So therefore, the manganese 3 are likely paramagnetic in this ferromagnetic, are likely paramagnetic at low temperatures. Okay, so that was the understanding of magnetism here, right? We have this kind of manganese 1, manganese 2, and then we have a paramagnetic manganese 3 here. So although manganese 3 here is paramagnetic, however, it really works as a it actually works as a medium to mediate manganese 1 interlayer coupling. So Igor, he was able to help us to understand this rich and complex magnetic phase diagram here. So the idea here was, I would say the idea here was because the manganese 3, so you can say based on this Hamiltonian, because the manganese 3 will, the manganese 3, which is here, right, it will interact with manganese 1 on top and also manganese 1 on the bottom, right? So therefore, the manganese 3, it turns out, it mediates a ferromagnetic, it favors ferromagnetic coupling. However, the manganese 1 super exchange interaction, it always favors antiferromagnetism between the manganese 1. So therefore, there is a competition between the manganese 3 mediated ferromagnetic coupling and the super exchange, which favors the antiferromagnetism. So therefore, because of this competition, right? Because of this competition, you will be, once you have more and more antimony doping, that just means you have a stronger, the second term becomes stronger and your compound, you know, the ferromagnetic coupling wins. And then if you cool your temperature, your manganese 3, which has this kind of paramagnetic, right? Therefore, it will follow a QoS law. So once you cool down the temperature, again, your manganese 3 magnitude goes up, right? Therefore, again, your ferromagnetic coupling wins. So, you know, this Hamiltonian can help us to understand this phase diagram. And then mainly it's just because of the competition between the direct manganese 1 antiferromagnetic super exchange interaction and the manganese 3 assisted manganese 1 ferromagnetic interlayer coupling. So in the next couple of minutes, I will talk about the effect of the defects on the band topology. Okay, so the thing is, how robust the non-trivial band topology, and therefore the associated emergent phenomena will be against the defects, right? So that's, you know, once we talk about the QH business, it's always like, you know, defects really play a role there, right? So you know, the thing is, as you can see, the crystal structure of this kind, the real compound, you know, the real crystal has complicated defect chemistry here, right? You have vacancies, you have anticides, right? So it is impossible to construct a structure model to reflect the real chemical defects, right? So what we can do is we just tried to approach this problem in two limiting cases. The first case is the so-called defect-free ideal case, right? So from this case, when we use this defect-free, which is assume there was no defect, and then Tyrone did a band structure calculation, it turns out in all doping levels, right, Z4 is equal to 4. So for all doping levels, the ground state is a ferromagnetic axion topological insulator. But we have defects, right? So next, to simplify the problem, we assumed 16.7% of manganese 2 anticides, right? And we used the ferromagnetic configuration. And now the band structure has changed much, right? So in this exaggerated periodic manganese 2 anticides case, you can see all band gaps are greatly reduced, right? But what we can see here is, we can say this band inversion, right? The band inversion, it seems like it still persists up to the intermediate doping regime. Okay, so the DFT calculation actually shows some robust band inversion here, right? Which again, it suggests that the long travel topology is likely robust against the anti-set defects here, and especially at the low doping levels. And for this doping level, the band structure calculation even suggests a magnetic wild semi-metal state. So here is the summary of the talk. Hopefully, I have given you an overall picture about the so-called manganese 1, bismuth 2N, tellurium 3N plus 1 family, right? So 147 and 1610 are antiferromagnetic topology insulators. 1813 is the first intrinsic ferromagnetic axion insulators. And they provide a promising material platinum to realize QAH and QSH with low fields or even without fields. And the anti-set disorder increases with the antimony doping. And as you can see, we got a this kind of anti-set disorder can tune the magnetism and the band topology, right? So it can, because of this manganese-mediated ferromagnetic interlayer coupling, therefore we were able to see a rich magnetic structure, magnetic phase evolution here. And the long travel topology turns out to be robust against the anti-set disorder, especially in the low doping levels, and in the intermediate doping levels, we found a possible magnetic wild semi-metal state here. Okay, so that is the end of the talk, and thanks for your patience to be here. And I just want to add one more sentence. As you can see from the whole period of my talk, collaboration is the key, right? So from material design and synthesis to magnetic, to the physical property measurements, to the identification or refinement of the magnetic structure, to the APS measurements to identify the band topology, to the DFT calculation, right? So we really need a team effort to really understand the material. Okay, that's it. Thank you.
All right, I'm clapping with my hands here, even if I'm the only one you can hear. That was an awesome talk. Thank you so much. I'm guessing there's probably a lot of questions from the audience. I know I have many, but let's see who we've got. You can raise your hand or use the chat or start shouting into your microphone. Anyone?
I think everyone's trying to find their unmute or the raise hand button.
Yeah, I know. Well, if anyone's still thinking, I had, first of all, I love how you got your phase diagram there, your electron phase diagram. Was it intentional to make it look like it's a diagram of like the ocean drop off, like a beach?
No, it's just, I love those colors.
Okay. Yeah, it makes me feel like I'm at the beach. It's great. Get the pink sunset.
Oh, thank you. Thank you for the artist's eyes.
No problem. At least my eyes. I was really interested in all this stuff with the disorder because it does something that you wouldn't really think about until you showed it to us. If I'm understanding correctly, the bulk properties are being moderated by the defects, but it's not just because it's affecting, local things up band filling. It's because of the exchange. Is that right?
Yes, that is right. So initially we thought, I would say, yeah, that part okay. I would say that's two parts, right? The first part is, our question is, why do we see an extra ferromagnetic state, right? Why do we have this rich magnetic structure there? And then to answer that question, we believe it was because of this manganese 3 sublattice, which mediates a ferromagnetic coupling between these two sublattices, between the manganese 1 sublattice. So that was the understanding of why we have an extra ferromagnetic phase and why the system finally becomes a ferromagnetic, right? But then from the anisotropy part, which is, let's see, which you can say based on this MH curves, you can see actually, I didn't talk much in the talk, but if you look at this based on the MH curves, actually our, the statue, I will say the field for the manganese 1 to be fully polarized actually decreases with the increase in antimony doping. So what does that mean? That just we did some anisotropy parameter calculation based on the MH data. It turns out that indeed when you dope antimony inside, your anisotropy parameter drops. So I mean, when you dope it, initially our idea was just to change this anisotropy parameter, but it turns out it was not just what we thought, but rather because of this doping introduces many more antacid disorder, and this antacid disorder have an X-ray exchange interaction term. So therefore, it's not just a local environment, local manganese environment change, but also a change the chemistry, the defect chemistry also as a result it changes the exchange coupling here. Does that answer your question here?
Yeah, no, it does. I mean, it helps me to kind of frame it all. So the point is that you come in with an idea about what your degrees of freedom are, but there's an extra degree of freedom you have to consider here.
Yes,
Maybe
yes,
it's actually
right.
more than 1 degree.
Yeah, initially when we started this project, I never expected it's going to be such a big one. So, and then it turns out that it's not just change the local environment, they also introduce anticides, and then one more exchange interaction enters a little bit mess.
So,
however, it's interesting. Yeah.
I was just, so I guess my more like my deeper interest here was about how you characterize that environment. You mentioned neutrons gave you a refined occupancy. Was that just based on a crystallographic model?
Yes, yeah, very good point. Actually, so to characterize the anticides is actually pretty difficult. I would say difficult in the sense is they are van der Waals materials, and somehow X-ray diffraction, usually X-ray diffraction for van der Waals materials, there are some small banding, whatever. The X-ray are the X-ray pattern or not. There was always some distortion of this Bragg peak, right? And then for neutron scattering, you can say actually the neutron scattering for the pure 124, for the pure 124 and 147 neutron scattering, the anticides refinement, if you put anticides in that one as actually it won't give you any. So it is within the the measurement error bar of this neutron HB3A. However, there was one way that it turns out is you can actually use the MH curve. You can use the MH curve as a kind of idea here. So do I have that part? Because of the time limit, so I didn't show that part. However, I can just have a rough talk here. So if you have a three manganese sublattice, then when you apply magnetic field along the Z direction, you are going to see a manganese 1 fully polarized. And then you are going to see a second step, which is your manganese 3 fully polarized. And then you are going to see a third step, which is the manganese 2 fully polarized. Therefore, just based on these little steps, as you can see here, right? This is one manganese 1 fully polarized. This is one manganese 3 fully polarized. So based on the difference between this MH data, we were able to have a estimation about the manganese 1, manganese 2, and the manganese 3 anticides here. So actually this one, it turns out to be a, be a good way to have a rough estimation about this anticides concentrations.
Okay. Wow. So I've got more people raising their hands, so we switch to them. I was going to get to talking about magnetic PDF, but that might be taking a little too deep for right now. So let's take some of these questions.
Sure.
But we can talk about it later. Let's see. First on my list is Chang Chen.
Hello.
Hi, Professor Lee, thank you for the nice talk. So I actually have a question about the calculation. So right before your summary slide, you show the band structures in the presence of defects. So do you know, are they computed with some kind of supercell method or with some other?
Yes.
Like a virtual crystal approximation?
Yes, they use the supercell.
So do you need to do some kind of average about the defects location or?
Yes, right. So you can say actually what happened here is, again, even if we consider the anticides, right, we put in 16.7% of manganese anticides, it still doesn't represent the real crystal structure. Why is that? Because this anticides is not random anticides, but rather it is so-called periodic anticides, right? So you choose one manganese atom, put it in bismuth, and you choose one specific bismuth site, and you put it in manganese, right? So I would say this, yeah, this is definitely a good, but there was from the DFT part of view, it's really there is no better way forward.
Okay, thank you.
Yeah.
Cool. All right. So Mahesh, I think you had a question.
Excellent talk. This is Mahesh Nipani from ARL. So I have to follow up this question about this manganese anti-side defects that we have in theory here. So I just noticed that all the manganese sites are within one quintuple layer in this model, right? Do you expect same behavior if they are in different quintuple layers?
Yeah, very good point, right? So still, again, in reality, right? In reality, we are saying manganese 1, and we are saying manganese 3, and we are saying manganese 2. And all of this doping, all of these anticides are just random anticides. There is no anticides order or whatever, right? However, again, for band structure calculation, you just couldn't mimic, you couldn't model the real messy chemistry here, right?
Mm-hmm.
So what we have to assume is we just forget about the manganese 3 anticides here, and we only focus on manganese 1 and manganese 2. And even for manganese 2, as you can see, actually I don't have that, but I can say, based on our MH, just now, based on the method I talked about the MH, how can we go from MH to get the antacid disorder, right? It turns out the antacid disorder for both manganese 3 and manganese 2 in this family are actually below 8%. So it's much, much less than the pure manganese antimony 2-4. It's much, much less. So therefore, that's what we say, we are actually exaggerating the antacid effect here. We don't have a 16.7% of antacids, but rather we are less than 8%. Yeah. Thank you.
Great. And I have one quick question about, you briefly mentioned that there might, because of this system is van der Waals type, right? There might be some manganese they might want to form, and this van der Waals like intercalation, setup, right? Do you have any evidence of that, or there's no evidence of this manganese being in this van der Waals layer, spacing between two quintuple layers?
We don't think so. Okay, we don't think there is. Okay, again, that will be something from this paper. Yeah, they were able to measure the MH up to, let's see, 60 Tesla. So if you have one more manganese intercalation there, right? So therefore, if that's the case, you can see this is the manganese 1 fully polarized field. This is the manganese 2 fully polarized field. If I have a third one, I'm expecting to see one more stat here. But actually, when they go up to 60 Tesla, they did not see that. So I tend to believe there is no manganese intercalation here. Yeah.
Thank you. Thank you.
Thanks.
All right, so who else we got here? Any more questions from the audience? I want to say that, of course, if you need to go, you can. We haven't really decided exactly how long to take, so we said we can have some discussion afterwards. But if anyone needs to go, you should.
I guess I just want to thank Professor Nee and thank everybody for coming out. We're going to have another seminar in 2 weeks. Dr. Yafei Ren from the University of Washington is going to be our speaker. So please come to that as well. Additionally, if you have any suggestions for any material speaker in any field of the, in broader materials field, please do send those along to Jared or any other member of the science board, and just, we would love to have more ideas. Ideally, come spring, we'll be having these every week, and everybody from anywhere is very welcome.